Okay, well, good morning, everyone. My name is Mao Wang, and I'm from QuickLogic, and I will be your host. Thanks for joining us. Today's topic is Secure the Future with Post-Quantum Cryptography on eFPGAs, and our speakers are Valter from Xiphera, who will be talking about what is the post-quantum computing threat and how to design systems to protect against it. And Robert Dawson from QuickLogic, who will be talking about the eFPGA implementation of Xiphera security solutions. And before we start, if at any time you have any questions, please go ahead and use the Q&A feature button below to submit your questions. We will have a Q&A session at the end, and we'll try to address all questions then. Now, let's get started.
Hi, well, welcome all from my behalf also, and good evening or morning, depending on the location. And thank you, Mao, for the introduction. I am Valtteri Allekotte, and I'm a developer at Xiphera. So let's get started. First, I'm going to introduce Xiphera as a company real quick, because I'm sure that there's some new viewers among us. And then we're going to have a short recap on cryptography to understand what is the quantum threat and the post-quantum cryptography. And last, we're going over the hybrid model and some practical views. So Xiphera is a Finnish security company founded in 2017. We are Finnish-based, and we design hardware-based cryptographic algorithms for mainly FPGAs and ASICs, so fit programmable gate arrays or eFPGAs, and also application-specific integrated circuits, so ASICs. And all our products are logic only and have been designed in-house. And we, of course, have a committed roadmap to support future secure algorithms and protocols. So cryptography can be roughly categorized into two different categories. We have symmetric and asymmetric cryptography. From symmetric cryptography, AES is a good example. So both parties have already a shared secret or key, and they can use a symmetric cryptographic algorithm, example the AES, to confidentially send each other messages, and it's encrypted and decrypted on the other end. Asymmetric cryptography, on the other hand, is more like exchanging the shared secret or case. And examples from that category are ECC, RSA, and PQC. You will learn that later today. So in asymmetric cryptography, both parties can have a secret key or private key and a public key. You can derive the public key from the secret or private key, but you cannot get the private key from the public key. And basically, other party sends the public key, and it's a public information, and it sends to the other party, and then they can create a shared secret or key. Let's go over some asymmetric cryptography protocols or algorithms. So we have key encapsulation that could be known also as key exchange. So Bob will receive Alice's public key, and with that public key, he's going to encapsulate a secret to be shared. And with this encapsulation, Bob will create a ciphertext that can be sent over to Alice. And Alice can decrypt or decapsulate this shared secret or ciphertext and get the shared secret. But asymmetric cryptography can also be used in digital signatures and authentication. So Alice will have a message for Bob. She will sign it with her own private key and then send the message to Bob. And Bob will have Alice's public key, and with that public key, they can verify that the message was actually sent by Alice or signed by Alice. Now, what is post-quantum cryptography? So post-quantum cryptography is a collection of algorithms that are resilient against quantum threat. Quantum threat means that if there's a powerful enough quantum computer, it can use Shor's algorithm to break the traditional asymmetric algorithms like ECC or RSA. However, AES, so symmetric encryption, is not in danger. And these kind of quantum computers does not exist yet, but they can exist in the near future or in the future. But many authorities already today mandate that the secure systems will be updated to support post-quantum cryptography in the near future. Because already today, someone could record the messaging that is thought to be safe for now and break it when the powerful enough quantum computer exists. And with quantum post-quantum cryptography, we do not mean a cryptography done by quantum computers or a cryptography using a quantum mechanical phenomenon. This PQC, post-quantum cryptography, can be done with traditional computers or hardware. And the PQC has already started early 2000s, and the NIST actually started a competition to find PQC algorithms in 2016. Today, we are at that point that we already have a couple of draft standards available. So on the right, you can see the drafts of the standards of winning algorithms in the PQC competition. And there are 4 winners, and we are mostly going to focus on module lattice-based, so mathematical problem module lattices. And we have module lattice-based key encapsulation mechanism, MLCAM, also known as Kuiper before. And then we have module lattice-based digital signatures and authentication, and previously known dilithium. There's also stateless hash-based digital signature and authentication algorithm called Sphinx. And there is going to be another DSA algorithm also based on lattice problems. And we are going to have the final standards in the near future. So drafts were actually published last month, and and enough with that boring stuff. So let's go over the practicalities. I'm going to introduce you the hybrid model. The hybrid model combines the traditional, already really known to be secure standard algorithms, ECC or RSA, and combines those algorithms with PQC. So we have this key exchange or key encapsulation and digital signatures and authentication algorithms that can be used in hybrid mode. So basically in key exchange, we are going to exchange keys with PQC and ECC and use a key derivation function to actually get the used key. And for digital signatures and authentication, we are going to sign the message or document with both PQC and classical signing algorithm and verify both signatures. And with this hybrid model, it's really easy to add PQC to systems that already exist and use ECC and RSA. And eFPGAs for the win here, because it's easy to add and update the hardware. And as I said, many authorities already today recommend and even mandate that systems will be updated to PQC. And now when the draft standards are already here, and actually Xiphera have already launched a exclave family of PQC IP cores, including the MLCAM and MLDSA. It's a good time to already think this when designing a secure system. New system use cases could include a secure boot, root of trust, secure communication models, protocols, and of course the standard protocols in the future will also be supporting PQC, like TLS, IPsec, and some VPN protocols. So again, eFPGA is for the win here, because you can actually update these protocols and systems in the near future. Thank you. That was all from me at this point.
Thank you, Valter, for that. So now what I want to do is I want to follow on from Valter's discussion and talk about eFPGA and how that can solve some of the solutions with regards to integrating these algorithms into your solutions and products. So QuickLogic is a fabless semiconductor company, and we have a range of solutions that we can provide. These are varying from chiplets. If you look at chiplets, there's a way of providing die that you can stack onto a substrate, so you can combine processors, memory, serial interfaces, and eFPGA into a product and provide you a flexible solution very quickly. We can also do standard products, and we can do bespoke implementations of, for example, eFPGA and provide the end product. So our eFPGA IP, which is the main thing we're going to talk about today, is we use a tool chain called Australis, which enables us to automate the design flow for the eFPGA. And by doing this, we can dramatically reduce the time from as little as 3 months to generate a new IP core and a new fab process node using standard libraries. And by doing that, we can lower the cost and also increase the flexibility of customers looking at using eFPGA. QuickLogic itself has been in existence for over 30 years, providing FPGA standard products and also providing AI algorithms and software. And we're a leader with regards to the open source community, or active member with regards to open source for FPGAs. So not only can we provide eFPGAs that customers can implement into their SoC, but we also have a vast experience of integrating eFPGA into our own products or ASICs, where we have a fixed function or standard function, and we have included also eFPGA into that. So going back to, I believe it's about around about late 90s, early 2000s, we had a 64-bit PCI core with FPGA. And then going on from that, we've supported 3 of the main microcontroller families. So starting off with MIPS, then going to ARM, and more recently with ETH Zurich, and now the Open Hardware Group, we have a RISC-V core with FPGA. So if you look at the challenges that people are looking at when they're looking at adding cryptography into FPGAs or into their products, first of all, we have evolving standards. As Valter mentioned earlier on, the spec is still being refined and tuned, and I'm sure once you get the first release out, there'll be ongoing revisions of the specifications. So Valter used a very interesting comment, a crypto agile solution. So what you want to do is you want to have the ability to either change the algorithms you're using or update to different standards based on your customer requirements. At the moment, there's no current off-the-shelf solution to integrate these new algorithms into, or new encryption and decryption algorithms. And if we look at what has happened over the last 12 to 18 months with the supply chain for standard products, you've seen lead times extending or supply constraints. You've also seen significant price rises in some ASSP-based solutions that are in the market. And if you're using external discrete components to connect to your main system, then you open up additionally external buses that potentially could be used for side-channel attacks. And you may also have a requirement to address unique operating environments, whether that's defense, automotive, or other particular requirements you have in your system. So what we have is we're talking about eFPGA here, and eFPGA provides a hardware flexible and reconfigurable solution that can accelerate AI and machine learning workloads. So we've seen customers where they want to offload things like softmax and other TensorFlow or machine learning type algorithms into FPGA because of the fact that you can parallelize up data and do things in parallel. Talking mainly today about the security, so looking at encryption and decryption standards. And you also see that, for example, in IoT applications, there's a lot of requirements for adding some timing critical I/O, or because of how fragmented the market is, looking at adding certain peripherals for a particular marketplace that maybe your key product doesn't actually have. And the idea of it is the fact that you can provide changes to hardware at the speed of software. So very much like with regards to most processors, now you have something like a GCC compiler that you can use and port. The idea is the fact that you want hardware that has a similar design flow or similar way that you can quickly change the hardware and implement it in your device using HDL code, which would provide you the ability to update the hardware over the air or in the field. And by doing this, you can extend the life of your product and also enable you to open up additional markets that you maybe didn't realize. And by doing this, you can then reduce the need for costly hardware redesign. So an eFPGA has all the features of a field programmable gate array, but it is provided an IP block that you can then integrate into your SoC or ASIC. So you have an eFPGA IP block, then you'll have some form of configuration block. Here we call it the FCB, but this is just a configuration block that takes the bit stream from either some serial interface, could be some secure boot location, or it could be from the processor, but it sits on a memory bus and then allows that FCB to provide the configuration for the memory of the FPGA. Also, you have a design for test interface, so you can interface and test the FPGA block itself. And then this will typically connect to I/O or some memory bus or peripherals inside your system, along with an MCU. But by doing this, you have all the advantages of an FPGA solution that you provide, but also enables you to customize the IP to exactly your requirements. Enables you to take control of your supply chain, so you're no longer in requirements of what the major suppliers of FPGA would do, and maybe you're not a key market area for them. You're no longer exposed to external buses or pins, so that removes that area of weakness. And also you want the ability to be able to specify the exact IP requirements, whether that's the number of LUTs, block RAM, DSPs, or other features you want inside the product. So a typical flow would be the fact that you do some form of evaluation using traditional FPGA design tools. And using that, you pass some designs or reference designs through, or you look at the reference designs potentially that the IP vendor has. From that, you're able to define an IP with regards to the amount of resources that you have with regards to LUTs, blockram, and DSPs, for example. And then that is then generated by the IP vendor, and then you can then integrate it into your SoC. And finally, you're able to innovate by implementing your own hardware designs using the design flow again. The key issue with this is the generation bit in the center. Obviously, the longer this takes, then the less flexibility you have through this flow. So here's a typical example of a IP block. So what we have here is the CLB. Just imagine they are just a clumps of LUTs that are very highly coupled together interconnects. And then you have columns of blockrams, DSPs, and like, and they connect up to the outside world through GPIO or peripheral buses. So with that, QuickLogic has IP that is completely processor and fab agnostic. We can use the Australis IP generation tool to port to any fab process voltage within as little as 3 months. And we can also make late changes to your requirements. For example, if later on in your design cycle, you find that potentially the mix of the LUTs, DSPs, and blockram need to be changed, then we can do that within a few weeks of the initial port. And you may find that your DSP configuration maybe want to change, or you might want to increase the amount of blockram. We're an open contributor to the open source community with regards to things like Yosis for synthesis, VPR place and route, and FODAC, which is a graphical tool interface. And also we have provided cores, reference cores for the open hardware group. So we can provide ability to provide eFPGA IP, FPGAs, and chiplet-based solutions.
Yeah, sounds like eFPGA is a perfect partner for PQC. And I actually have a little bit questions for you, Robert.
Okay.
Well, how do you, or how does QuickLogic enable the customization of the, or specification of the eFPGA in their SoC platform?
Okay, thank you. Yes, so we have two tool chains that we provide. One of them is the fact of Aurora, which is a traditional FPGA design flow tool. And with this, customers can take their HDL Verilog, system Verilog, or the HDL code, pass it through the tools, and from the report files, we can get information, for example, like the amount of routing resources that they require in a design. We can do trade-offs with regards to generating new XML files that will have differing chain arrays of logic, and also the placements of the DSP blocks and the blockram, which they can then trial very quickly in the FPGA development tools. And from that, we can then, using the Australis tool, we can then actually automate the generation of the IP in the center part of it. Once we have an initial port to a fab, if later on in the design cycle, the customer finds some other requirement, then what we can do by running more designs through the tools, we can potentially very quickly change that and generate a new IP block for them without having to go back to the initial cycle, which you would do if you were trying to do this in a custom FPGA or a custom flow using custom standards, custom logic cells.
Yeah.
So Valter, that's how we solved that. How does Xiphera, or what problems do customers encounter when integrating PQC into the designs, and how can Xiphera help them?
Well, there can be like issues with interfaces or software. Well, software in general is a bad way to implement cryptography, but you have to interface your hardware crypto with software at some point. So we can provide interfaces to processors from the eFPGA logic, and we can interface that with different kind of standard buses, for example, and FIFOs or blockrams or anything like that found on the eFPGA. And we can of course then help customer to to integrate into their system. We talked about the hybrid model. We can give advice or help with the design on the security level and on the hardware level as well. And of course, the software, it needs to connect to software at some point. So we can provide drivers for OS or standard libraries for APIs and that kind of stuff. And that's pretty much it. Those are the problems. Yeah. And well, as I said, PQC could be implemented in software, but we don't recommend it. And it can be implemented in hardware, and we know that, and we recommend that, of course. So what do you think that are the key benefits for eFPGA over, for example, microcontroller, CPU, or ASIC, or traditional FPGA?
Sure. So if we take each one of those separately, so first of all, if you compare it to FPGA obviously can implement it. It's a reconfigurable hardware platform. But the real challenge with that is the fact you have external pins or buses in the system, which are a weakness or a point of vulnerability that people could do sidechannel attacks. You then have, obviously, if you look at ASICs are great if you have an existing standard that is stable and is not going to change. And obviously, we know with PQC, that's not the case. And then obviously with processors or systems, obviously there are always challenges with regards to implementing some of these in software, performance vulnerability, side attacks, and other ways of actually accessing what it is. Typically, a lot of these algorithms they use, or encryption algorithms, use a lot of bitwise or bit manipulation, which is not very efficient to be implemented in processors, and also the memory, because you're continuously accessing external memory or system memory, which is obviously a point of vulnerability. So looking at your solutions, or what you talked about, the hybrid model, do you have to already have ECC implemented in that, or?
Well, you could do both. We have experience that the ECC is already there. And of course, then we can, as I said, then we can simply assist the customer to implement the hybrid mode with MLCAM or MLDSA to have the hybrid mode, and PQC as with the already existing ECC or RSA. But of course, we can provide the ECC. We actually have a very large portfolio of other security solutions and IP cores, which you can see here. For example, we have the RSA and ECC there, and with the hybrid model there, there you can use the key derivation functions. So we have that hashing algorithms for the DSA problems, and we have protocols also, so which are going to be updated to PQC. So that is a good question. Good question indeed, but we can provide the ECC, or it can be already there. And with PQC, the key lengths are actually a little bit longer than with ECC, for example. So how can we mitigate this problem with eFPGAs? So we have longer keys that we need to transmit. The ciphertext is a little bit longer.
Yeah, that's a very good question. One advantage of FPGA and eFPGA is the fact that ideally you have internal memory, so block RAM that can store data. You can also store some configuration or some ROM tables, for example, using logic cells, LUTs. So that's very efficient and very hard to reverse engineer. And you also, because you have a vast amount of I/O pins in the array, you could connect externally some secure memory that potentially the eFPGA only has access to. or you could have it connecting to some secure memory that's not accessible outside the device. So there are a host of different ways that you can try and secure that key inside the device, or make sure only the FPGA has access to it. But you mentioned there about size of keys. What kind of size keys are we talking about?
Let me show. Let me show real quickly here. So here is the table I was looking for. So here you can see a comparison between the ECC and Kuiper, so MLCAM keys. So the security levels roughly approximates the AES security level on 128 bits and 256 bits. So on the highest security level on MLCAM, so we are talking about private key, a little over 3,000 bytes, and public key, which will need to be sent out, is 1,500, a little over, and same with the ciphertext. So public key and ciphertext, those will be sent, and those will be sent outside the system. And yeah, well, the all variants will still output the standard 256 long keys. So that is what will be used for the shared secret key. Yeah.
So thank you for that.
Thanks, guys. I think now we also have several questions from the attendees. And so what I'll do is I'll go ahead and start reading them out, and maybe either Robert or Valter can help. So the first one, I think this is a question for Robert. How does someone, I guess customers in general, figure out what eFPGA size they need, or how do they figure that out?
So we typically see two different types of customers. One customer potentially may have a set area or size in their SoC that they need to that they wish to use for eFPGA, or have free for eFPGA. This happens quite typically if we engage later on in the design cycle, and obviously then it's trying to fit the maximum amount of resources that they can into that silicon area. The other option, when it's earlier on, potentially the customer gets our Aurora design tools. They pass through some typical types of HDL designs that they've used in the past to gauge some form of requirements with regards to both area and also performance, because there's always trade-offs between area size and performance. As you increase the performance of the eFPGA, then typically you'll increase the area that takes in the device. So our toolchain allows you to start doing that, and then we can provide, like I mentioned earlier on, XML files that are very quickly, that are tuned exactly to the size array you're looking at. And then you can then use the existing toolchain we have to actually run the new your design through the new devices, virtual devices we create, and check the performance and area and fit for your applications.
Okay, thank you. Next one is says currently there are no relevant quantum computers, I guess, out there. So why do we need to care already now, or what is the business focus in terms of how to deal with that?
Yeah, well, I can maybe get that one, because I a little scratch on the surface on that one on my presentation. Well, we don't have the quantum computers yet, and nobody knows when they will be or if they will be available. But there was this point that you could record the most mission critical communication already today and store it for certain amount of years when you have the quantum computer that can break the whole communications where you have exchanged the keys, and then you can decipher or decrypt basically the message. So we should already be using post-quantum crypto if we really need these secrets to be secret for a long time. Another point is that the systems are they will be mandated to have PQC at a certain point. All these mission critical systems, I mean. So, for example, NSA and there's even a US law for it that mandates to have a roadmap for PQC in the most mission critical systems.
Okay, thank you. Next one, I think we have another one that says, how does these eFPGA IPs differ from in-house design programmable blocks? So the company designing the SoC just decide to make a small programmable logic block by themselves.
Okay. I'm not sure. Well, first of all, there's several things from that. First of all, it's in FPGA terms, yes, it's not a big device that's required, but it still is a reasonable amount of logic cells that you require. And one of the things that we would say we have is, obviously from our 30 years experience, is the fact of how you optimize the layout of that design to ensure you get predictable routing and delays. And also we have the toolchain supply background with it as well, that we're able to provide an end-to-end solution. So we not only can we provide IP, but also a complete toolchain. Yeah, I mean, it's really, you're buying the speed of getting something into the marketplace by using our IP and having a known tested solution, comparing to trying to implement something yourself.
Okay, thank you. There's another question where it says, where will the hardware be placed for asymmetric base encryption case? Would it be on the side of public key or private key, or where would the hardware be placed?
Basically, what I got that, for example, in MLCAM, you would generate the key pair, so secret key and public key with FPGA, and then send the public key to a host or a client or the other party, maybe outside the whole system, or it could be a other component, for example, in the system. And the other component with software or hardware would then use that public key to generate the shared secret and generate the ciphertext and send it back to the hardware or eFPGA, and where it would be again decapsulated, and then you end up with shared secret K with both systems. I don't know if that answered the question. Hopefully, yes.
Okay, thank you. Then the next one is, could I have two different bit streams, potentially two different security algorithms for the FPGA, and then be able to load them at different times?
Okay, I'll take this, Valter. Yes, yeah. You can. You would need to go through the reconfiguration of the IP block, but yes, you can change the configuration. You could have many different images that you could boot from and reconfigure the hardware.
Yeah.
Potentially, you could even have. We talk about one eFPGA block, but potentially you could have multiple eFPGA blocks in your design, and you could keep some alive and reconfigure other blocks as well. Yeah,
that's actually a really practical way. If you cannot into an existing device, you cannot get cannot fit ECC and PQC both. So
yeah, because that is typical a trade-off you want to make, is you don't want an FPGA that's eFPGA that is so big that it can do everything. You typically want to switch its functionality based on what task your system is doing at that particular moment.
Okay. Next one is how does someone use PQC with secure boot? That's probably for Terry.
Yeah, well, that's a really good question. I can maybe go through. So basically, you would use MLDSA for that. You would only care about the authenticity and integrity of the boot file that you are going to be loading into the, for example, nesting device you have after the eFPGA. So eFPGA would be loading something to somewhere. So you would sign the boot file with the PQC algorithm, and with the eFPGA you could verify that with the public key, and then if the verification is completed okay, so the verification is intact, and then you can continue and boot up the device and load the binary into it. So that would be the use case.
Okay, thank you, Valter. There's another one. I think this one's for Robert as well. The 3 to 4 months design cycle is repeatedly mentioned. How much faster is this design cycle with QuickLogic components versus without?
Okay, so just want to clarify something. That's not the design cycle to integrate in PQC into your system. That's because that can be done very quickly based on the platform or product you already have. But what we're talking about there is generating a new eFPGA IP core based on a fab or process or standard cell libraries that we haven't previously ported to. And this is just to create the IP. If you look at the way that traditionally FPGAs and eFPGAs have been developed, then it's typically using custom cells and physical, doing a manual placement of the design. And that can take typically anywhere from 9 to 12 months to actually achieve. And obviously the cost is associated and related to that. So one of the advantages we have is because we've automated that flow, we can get a first pass through within 3 to 4 months, depending on how much customization you want. But then if you wanted to, for example, change the array size, so you wanted to increase the number of logic cells or move the DSPs or block RAM, then like we said, we can do that. Once we have a test version already gone through, we can make those changes within a very short period of time within a couple of weeks, which you couldn't do if you were doing a standard custom layout, manual layout, because you'd have to go back through the process and repeat a lot of the work you've previously done.
Okay, thanks, Robert. And I think we have this one more. That actually there's a couple more, but one more here is why would we use a hybrid crypto system KEM with ECC while we can use a PQC key exchange algorithm to share the secret key?
Yeah, well, that's actually a really good question. Maybe I wasn't going through enough the hybrid model. So the principle is that you would have two set of algorithms that you can trust. So if either one gets broken one way or another, quantum computer or a fault in the algorithm, then you would still have the other working algorithm. So for example, in the key exchange, we have gone over this previously. So you would exchange keys with both ECC and MLCAM. So you would actually do two key exchanges and combine that key and use that key for the bulk encryption or anything else that you do with the shared secret. So you would have the best benefits of both. And while the PQC is looking promising, or the standards that we are seeing, there could be some kind of attacks that could still prove to break these PQC systems even without the quantum computers. But ECC has been there a long time, and there is a very, very strong academical background on that one. So I think it will be safe to use hybrid systems that use ECC and PQC. Hopefully that answered the question.
Okay, I think we have just a few more minutes just for a couple more. How different is eFPGA versus eASIC?
Okay, I think eASIC is something that's being promoted by Intel, and they say it's very similar to an FPGA flow, but from my understanding, what that is taking almost turning the FPGA into almost like a gate array. So it's hardens the routing resources and provides you a lower powered solution, potentially, and lower area solution than a normal FPGA. But the challenge with this is, as far as I understand, first of all, you're limited to Intel fabs, which is fine. That's one thing if you want to do. But the other thing is the fact of, from my understanding, and I could be wrong about this, is the fact that it's not reconfigurable. Whereas an eFPGA is. I can go and check and come back and confirm that after this call, but that's my understanding to the difference is that, for example, the Intel eASIC is restricted to one fab, whereas eFPGA is completely open to any fab. We can port it to any fab. And secondly, my understanding is, even though it uses an FPGA approach and you prototype in FPGA, it then hardens the routing of that to make it into an eASIC. Whereas with an eFPGA, you still have field-based upgradability.
Great. Thanks, Robert. And I think we'll just take the last one. How do you face a quantum plus sidechannel plus AI attack in the future?
Well, basically, you have to take sidechannel into account already today, or yeah, it has been there since the beginning of hardware crypto. So of course you have some measures to mitigate that problem. So there should be as less information going outside as possible, and we have certain anti-sidechannel protections already in place, and we are implementing more as there will be more research on the sidechannel of PQC algorithms and ECC also. And AI attacks, I'm not an expert on that area, so well, basically that could at least speed up these attacks, sidechannel or regular attacks. But Robert, can you comment something about eFPGA sidechannel protection? I think you scratched the surface there in your presentation.
Yeah, sure. I mean, I think, as you mentioned earlier on, is the fact that the key, first of all, is the most critical piece. Your private key is the most critical piece of information, and obviously, if that becomes available externally, then that is disastrous for you. Any encryption standard you want to use. So obviously, that needs to be protected inside the device and not being passed outside. And there are ways you can do that. For example, like I mentioned earlier on, you could have it in as part of the bit stream that is loaded into the logic. So it's not even in memory, it's actually configured in parts of the LUT as like a ROM. But also you can have, you want to ensure that as much data is internally to the device as possible. So two ways of doing that. First of all, having internal memory of the FPGA or eFPGA, but then also by the fact that it's part of an SoC integration means that you can avoid, or not avoid, but you have less points of data attack that you can actually have from externally, because you don't have many external buses and definitely don't have significant unencrypted data coming out or the keys accessible.
Yeah. Yeah, I completely agree.
Okay, well, thank you guys for your presentation, and thanks to all the attendees. So both Xiphera and QuickLogic, we are partners and worked together in a joint solution here. So for people who are more interested in a secure security solution that could be implemented on an eFPGA, please contact us via either directly from at QuickLogic or from Xiphera, depending on whether your questions are more related to FPGA or to security. We also will be sending out a link to this recorded session for you guys to review at your own time, as well as we'll be emailing you a white paper on this. And we want to thank everybody for attending, and hope to hear from you if you are interested in our solution. And thanks everyone, and have a great day.